Okay, hello everyone. So we're gonna discuss a new topic today. It's called Gauss law. Gauss law also it's like a convenient way to find electric fields due to different shaped objects. Like so far, what we know is how to find the electric field due to point particles, point charges. Like for an example, if there's a point charge Q, and we know that at a distance r the electric field is kq over r squared, or we can say electric field is 1 over 4 pi epsilon q over r squared. Depending on the medium, sometimes we write it as epsilon, sometimes if it is vacuum or free space we put epsilon naught. So either way, due to a point charge, we can find the electric field using this equation. This is the same thing. You just replace this constant k with the more fundamental numbers. But if the given charge is something like this, like let's say a charged sphere, a solid metal sphere, and you want to find the electric field at some point over here, we can't use the above equation, right? This is only for point charges. Now a solid sphere with some radius, this is not a point charge anymore. And so let's say, yeah, so we have to, it's like a collection of point particles, right? So we have to come up with some different technique. It can be something like this spherical shell, where the substance is over here, inside is empty, and then we say that okay, that it is charged to a charge of q1, this will have charge of q2, something like that, and you want to find the electric field, let's say over here on the surface. So we need these kind of calculations, but the above equation doesn't help. Another example I can think of is a cylinder. It can be a solid cylinder like this. It can be a cylindrical shell, like a hollow cylinder. It's empty inside. So when it comes to these kind of cases, we can use this Gauss law and find the electric field. Gauss law also has certain limitations. The objects should be symmetric, means they should be simple geometric shapes, like a sphere or a long cylinder, a uniform cylinder, a spherical shell. If we have like a odd shape object, like not that symmetric, it's not a simple shape, and finding the electric field at this point gonna be very difficult. So we're not going to try these things. We're going to limit our discussion to spherical, or not really spherical, sorry, simple geometric shapes. Okay, so it will be mostly solid spheres, spherical shells, solid cylinders, and hollow cylinders, right? So we're going to limit our discussion to these things, and we will talk about how this Gauss law works. All right, so to start with Gauss law, we're going to introduce a new term, electric flux. When we talk about Gauss law, we need electric flux in order to understand this. We'll look into some applications, these things. This topic we'll see depending on time. What is electric flux? Now imagine you have a point charge, positive charge. Now positive Q. Now electric field is symmetrically going outwards. Alright, now Let's say I want to find the electric field at some point. If I draw a circle going through that point, now we say that I'm enclosing this charge using this surface, right? I draw this circle, a sphere around the charge. So I want to find the electric field at a distance r at this point. So take this distance as the radius. I'm drawing a circle, this dotted line, and then I enclose this charge inside that sphere I drew. So the electric field comes out from this sphere, right? In any point there's electric field comes out. We can draw like thousands of lines. Now if I take some area, the surface area on this sphere, here's the area. There's an electric field coming out. When you multiply this electric field and the area I selected, this product is called psi or electric flux. This is the idea of, this is the simple definition of electric flux. Electric field that comes out through an area multiplied by the area. Electric field multiplied by the area is called electric flux, and the symbol is this capital psi, Greek letter psi. Okay, there's more to this definition. We say that the electric field that is coming out perpendicular to the area. But in our discussions we will have perpendicular electric field. We will not use electric fields with any other angles, make things a little difficult. So the right definition, the complete definition is the perpendicular electric field multiplied by the area. But for our use, let's just say E field and area. You multiply them, you get the flux. All right. So what is this flux? Why is it important? Let's see what the next slide says. Okay, so well, don't look at this yet. Let me explain something before that. Okay, make some space here. Alright, so we have this point charge and we draw this circle around it, right? We want to find the electric field at this point, so we took that distance as a radius and we draw a circle around it. Now when it comes to the Gauss law, my question is find the electric field at this point, so I draw a circle. We call this the Gauss surface. Gauss surface. So I draw a Gauss surface. This Gauss surface is covering this little charge inside it, right? This is my charge Q. The Gauss law says flux coming out through a Gauss surface. Now here the electric field comes out, we say the flux coming out. The total flux coming out from a surface is equals to the charge inside that surface. So we can say charge inside divided by epsilon, the permittivity of the medium. This is permittivity. We have mentioned this word before, permittivity of the medium. So that's what this slide says. So let's go here and see. It's written in a different way. You see that it, instead of psi, they have written E times dA. This is a calculus kind of way of writing it, but for our calculations, let's keep it simple. The flux coming out, or electric field multiplied by area of the Gauss surface, right? Gauss surface area. This is area of Gauss surface. E times A equals Q inside. Here they have used the word enclosed. Same thing. Enclosed is a better word. The charge enclosed by the Gauss surface. So you can even write Q En enclosed divided by epsilon or epsilon naught. Whatever the epsilon number given, we put it there. So this is what Gauss law says. Electric field times area. Area of the Gauss surface is equals to charge inside that Gauss surface divided by epsilon naught. So if you want to find the electric field, we take the equation, take A to the other side, we have Q enclosed over A times epsilon naught gives us the electric field. Okay? Alright. Let's try some applications, some example problems. Okay, so we talk about this. Gauss law says electric field at a given point multiplied by the Gauss area going through that point equals charge Q, you can use little q if you want, enclosed in that surface over epsilon naught. So let's use this into a point charge example. Let's say we have a point charge Q, and you want to find the electric field at this r distance over here, electric field. So traditionally, using the method you learned previously, what you would do is you write electric field is K times Q over r squared, or you can write 1 over 4 pi epsilon naught. We replace K with that, Q over r squared. Now this is a standard equation given for a point charge to find the electric field. Right. So let's use the Gauss method. Now we're going to do the same thing with Gauss method. So we have this charge Q. We want to find the electric field at a distance r. We need to find the electric field at this point. So what we do is we draw a circle taking this distance as the radius. Why do we draw a circle? Why not a rectangle? Why not a square? Why not a triangle? Why circle? So the Gauss surface we draw should represent the shape of the charge that is inside. So if it is a point charge, still it's a round thing, right? It's a sphere. So your Gauss surface has to be a sphere, a circle. Now remember, this looks like a sphere, but this looks like a circle, but this is actually a spherical surface, right? It's a spherical surface. It's 3D because this point charge, it's not like a dot, it's like a 3D dot. It is a dot, but it's in all dimensions. It's in all 3 dimensions. Okay, so we draw this spherical surface and then we start here. E times the area of the Gauss surface equals charge trapped inside enclosed divided by epsilon or epsilon naught. E times, okay, so I can leave E here. I will take area to the other side. Q enclosed, area times epsilon naught. Now, for a sphere, for a spherical surface, what's the area? The 3D area. If it is a circle, the area is, we all know that pi r squared. But in 3D, in 3 dimension, for a solid object, for a solid sphere. What's the surface area? It's 4 pi r squared. Right? That's the area. So E equals Q enclosed 4 pi r squared epsilon naught. Now if I move the terms back and forth a little bit, I can rewrite it this way. I can isolate this guy 1 over 4 pi epsilon. I take epsilon with it and write the rest of the terms separately. Q enclosed over r squared. Isn't this the same thing as that previous equation? Gauss law gives you the same thing, right? This is just another approach. This is a more geometric kind of graphical kind of approach, which is really useful, not for this particular application, for this example, but other examples. Okay? Alright, so let's try a few examples. Okay, so let's move on and try some examples. I'm going to make the thing bigger. Okay. Alright, let's try an example. A familiar one, a point charge. This equation really not necessary for point charges, but just to show that it works, let's do one. Let's say we have a point charge of 2 microcoulombs and you want to find the electric field 3 meters away from it, this point. Electric field 3 meters away. Traditionally what you would do is you do E equals kq over r squared, 9 times 10 to the 9, q, that is 2 times 10 to the negative 6, r squared, 3 squared, and then simple numbers cancels out. We have 2 times 10 to the 3 newtons per coulomb, right? Electric field at that point is this. Now let's use Gauss law. Here's the charge, 2 microcoulombs. We need to find the electric field at 3 meters. So we take this point and draw the Gauss sphere, Gaussian surface. And then we write E times area of the Gauss surface equals charge inside over epsilon naught. Okay, so what's next? E times area of a sphere is 4 pi r squared. R is what is r? 3 meters, so 9 squared equals q inside 2 times 10 to the negative 6 divided by epsilon naught. Now the value of epsilon naught, I don't remember whether I gave it to you or not. Just 1 second, let me check this message real quick. Okay, again, I don't remember whether I gave the value or not, but we can easily find that out. Epsilon naught, the permittivity of free space, is 8.85 times 10 to the negative 12. So if you do the math, E equals, take all these things to the other side, we have 2 times 10 to the negative 6, 4 pi times by r squared, 3 squared, not 9 squared. 4 pi times 3 squared times 8.85 10 to the negative 12. You do the math, you get the same answer, 2 times 10 to the 3 newtons per coulomb. Things will cancel out nicely. Okay, so now this is with mathematics. We can do it without all the numbers. We can cancel out things easily. The other thing is this permittivity, this epsilon naught. Depending on the medium, it will have a number. Now we are talking about the regular atmosphere, so epsilon naught takes the value of 8.85 10 to the negative 12. This is the number we generally use. Sometimes if things are in different mediums like underwater or inside certain substance like inside plastic or inside human body, this number will change. We have to put a different epsilon for that. There's epsilon permittivity tables, so we can easily find the number. Alright, so going back to this calculation, going here, I can do all this without messing with too much with the numbers. So we have EA equals Q inside over epsilon naught E times 4 pi r squared equals Q enclosed over epsilon naught. Bring it to the other side. E equals Q inside over 4 pi r squared epsilon naught. Move the terms a little bit. So going here, E equals Q over Q inside over, bring this epsilon to the front, 4 pi epsilon naught r squared like we had before. This part, this is 1 over 4 pi epsilon naught, which is just K. So you can just put the value of K over here, which is 9 times 10 to the 9, and then you have 2 times 10 to the negative 6 and divide by 9 squared. It comes back to this original equation. It reduces to that and you get the same answer. Or you can take this route over here and plug all the numbers you want and find the same answer. Okay, so that is just a point charge. Now the actual power of this method, Gauss law, we can see the actual power when we use things other than point charges, right? For point charges it really doesn't matter. So let's try one of those examples. Alright, let's say this time we have a solid sphere. It's a metal sphere, so let's say a metal radius equals 5 centimeters, and we're going to put total charge equals 3 microcoulombs, and I want to find the electric field. Find E 15 cm from center. So I want to find the electric field. Now this radius is 5 centimeters. This is a solid metal sphere, and we put charge of 3 microcoulomb into this thing. So this thing is charge, and I want to find the electric field somewhere over here, 10 centimeters, 15 centimeters from the center, right? What's the electric field? Now for something like this, we really can't use that previous equation. We have to go with Gauss surface method. So what do? We write EA equals Q over epsilon. This is my Gauss surface. I draw a circle. Because this is a circle inside, I have to draw a circle to symmetrically cover that. And then E times the area of this Gauss circle, not the actual object, but the Gauss circle. So E times area, which is 4 pi r squared, 15 centimeters, 0.15. Area is always measured like, you know how to find the area, right? This distance is 15, so that is our radius. 0.15 square equals charge inside the Gauss surface, which is 3 microcoulomb. 3 times 10 to the negative 6 divided by epsilon, which is blah 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 8.85 10 to the negative 12. So here's the numbers. Now we can find the electric field. Take it to the other side, do the math, which needs a calculator, and if I do that, it's going to take time, so I'm going to pause this. I have 1.19 times 10 to the positive 6 newtons per coulomb. That's the electric field at this point. Okay, alright. I want to find the electric field on the surface, right here on the surface. So what do? So here's my charge sphere. Charge is 3 microcoulombs. Radius is 5 centimeters. Let me draw a bigger diagram, so it makes things a little easy to see. 5 centimeters, 3 microcoulombs. I want to find the electric field right on the surface. So I'm going to use Gauss law. I need to draw a circle, a Gauss surface that goes right over this, right? Because Gauss surface also going to be 5 centimeter radius. So EA equals Q over epsilon naught. E times 4 pi, this time Gauss surface also has the same radius, 0.05 squared, equals charge inside 3 times 10 to the negative 6, divide by 8.85 10 to the negative 12. Do the math, pause again. I have, I get 10.7 times 10 to the 6 newtons per coulomb, or 1.07 times 10 to the 7 newtons per coulomb. You see, the electric field gets bigger. The closer you get, it gets bigger. So there's a higher electric field over here. There's some in-between electric field over here. If you measure it over here, somewhere here, you draw a big Gauss surface, you'll find a very tiny electric field. Okay, so as long as the object is a simple shape, Gauss method is really helpful. Alright, now I want to find the electric field at 3 centimeter distance from the center. This was, the previous one was 5 cm from center at 3 centimeters. Now this is a metal sphere, a solid metal sphere with radius 5 centimeters. Its charge is 3 microcoulombs. My question is, what is the electric field 3 centimeters from the center? So it's going to be an inside point, 3 cm over here. What do you think? Will we get a bigger electric field, a smaller electric field? What do you think? So the method is this again, EA equals Q over epsilon. I'm going to draw a circle, a surface inside, so I can put the area of that thing, that will be 4 pi 0.03 squared, equals Q inside, charge inside this Gauss surface that I drew. The previous ones were outside the sphere, right? 15 centimeters was definitely outside. Even the 5 centimeter circle is on the surface, so the entire charge is covered. Now what happens? Where is this 3 microcoulombs? Is it evenly distributed? Is it here and there? Are there any charges inside? How many charges trapped inside this dark area? Now here's the thing. I told you this is a metal sphere. I forgot to mention the word conducting. Let's assume that this metal is a good conductor. I should have said conducting instead of metal. It's a conducting sphere. Conducting means charges won't remain inside. They are all going to be on the surface. When charges are on the surface, there's nothing inside. When you draw this Gauss circle, there's nothing inside. It's zero. Electric field becomes zero. You don't even need to do any math. Right? So that's the beauty of this theory. Now here's another interesting situation. I can give you a non-conducting or insulating sphere. Non-conducting sphere. And I say that there's 3 microcoulombs. This is also, radius is 5 centimeters. And I say charge is 3 microcoulombs evenly distributed. So if it is non-conducting, like a piece of wood, a wooden sphere, I can place charges wherever I want. I can place them on the surface. I can place them inside anywhere I want. When I say evenly distributed, there's charges on the surface and there's charges inside throughout the volume. So if I ask electric field at 15 centimeter, that's an outside point. So you draw the Gauss surface, charge inside is still 3 microcoulombs. If I say find the electric field on the surface, you draw the Gauss surface along the surface, charge inside is 3 microcoulombs. If I say what the E field at, let's say 2 centimeters, less than the radius, inside the circle over here. Now when it comes to charge inside, you really need to calculate this. If the whole thing has 3 microcoulombs, this much, how many microcoulombs? It's going to be some ratio, right? So that's something you need to figure out. So I'm going to stop right there. I'm not going to, I shouldn't be overloading too much information. Think about this last part. If you're given a problem like that, what to do? So we'll discuss these example problems in class. Alright? Okay. Thanks everyone.